Well, it's great to be here. It's always nice to be in Santa Barbara, right near the beach. Of course, here we are indoors in this gray room, but it's still nice to be here. And great. So the topic of this talk is optical cavity quantum electrodynamics, optical cavity QED. It's, in a sense, a pretty old topic, right? I mean, I think already in the very beginnings of quantum optics, these kinds of systems were considered. And what makes the cavity QED system is that, to some degree, it's much simpler than, many-body quantum optics. In particular, it reduces the number of optical modes, largely, that a quantum emitter has to interact with. And yet, this very simple paradigm has found a lot of utility over the years, and a lot of it's retained our interest. And it's partly because there's just so many ways to kind of configure an experiment that would make use of optical cavity QED in some manner. And all of these are sort of playing out in a lot of laboratories around the world, including in mine. So I can just give you a little bit of a landscape of what we've been doing with these systems, and maybe try to convey to you the way I think about optical cavity QED. So one thing that we've certainly been hearing a lot about at this meeting is the thought that different quantum emitters placed within the same optical cavity can be made to interact with one another, and that's because we can inspire one quantum emitter to emit a photon, which is then fairly deterministically absorbed by another emitter, and that can convey a force or a spin flip or create some kind of gate or something, and that leads to an interesting many-body quantum system, and I'll tell you mostly about that topic. But we should also remember that these cavity QED systems are open, that these photons that are being exchanged by these quantum emitters are real and that they can leave, and that provides us with a little bit of a headache, but also a lot of other opportunities. So for example, optical cavity QED systems are useful as enhanced measurement devices, because you can really strongly induce a quantum emitter to place its information into an optical field that comes out efficiently into your detector. This was the gist of how we implemented mid-circuit measurement for a tweezer array using the cavity-enhanced capability of measurement. It's also possible to use these cavity QED systems as interesting light sources. So now that we're getting better and better at making interesting many-body quantum systems that live inside of a cavity, we can think about essentially like putting them through a facsimile machine, which I guess this audience is roughly old enough to know what it is, and turn that information into light, which then would come out. So we can think about, generating interesting quantum states of light, starting with some kind of quantum microsurgery on a material system, and then just zapping it into the optical field. And then we can also combine a bunch of these functions in the same experiment. So we can imagine the fact that a quantum system is shedding information to the outside world might be the basis of a feedback system. That feedback can be either constructed autonomously, so it's actually within the quantum system itself, the light kind of folds back and acts on the emitter, or it can be incorporating some kind of electronic controller that then changes the way in which the quantum system behaves. And so there's an opportunity now to think about many-body quantum systems that are under feedback. So optical cavity QED has a lot of utility, and to really make use of this paradigm, we need to learn how to place quantum emitters inside of a cavity and really control well how they interact with the cavity field. And in that regard, there's sort of been an advance over the years in how to do this. So for the first, 25-ish years or so of my scientific career, the approach was to get a big batch of cold atoms, maybe Bose condensed, maybe not, or something, and just sort of heap them into an optical cavity, and maybe some thousands or hundreds or millions of atoms or something are placed in the optical cavity. And that certainly led to a lot of wonderful science, but it lacked a certain level of control. You didn't know exactly where the atoms are located. You didn't know exactly how many atoms you're dealing with, and so on and so forth. Now atomic physics has advanced, and maybe you've been paying attention in some of the talks during this week, that this other approach of preparing a sample of at least ultracold atoms really has some very clear strengths, so that we can now take really a selected, a fixed number of atoms with essentially digital control over the atomic number, and place atoms exactly where we want to place them inside of an optical cavity. And that really is going to allow us to jump forward in optical cavity QED experiments. I would say that this is not altogether entirely new, because if I go back even further, I remember my postdoc experience, which was working in Jeff Kimball's lab, where I learned about cavity QED, and I'm quite indebted to him for all of my knowledge of and involvement in the field of quantum optics. And already back around 2000, when I was a postdoc, we were learning how to just trap atoms, sort of throw a bunch of sand into a cavity and try to catch a single grain in there. And that was a successful effort. So to some degree, I'm sort of going around in a big circle learning how to place a single atom inside of an optical cavity. But still, even in this experiment, whether or not an atom would be trapped and where it would be trapped and certainly how many atoms would be trapped was not really something that was under full control. So still, the optical tweezer approach is really a strong step forward for us. So we went ahead and built an experiment. Took a number of years to get this going, and it wasn't an experiment that we built specifically for this task. It was sort of repurposed afterwards to enable us to do these kinds of experiments. So to some degree, it's a more complicated experimental setup than it really needs to be. I think if we were to redesign this from scratch, we would build something that's simpler and has a much faster repetition rate and such. But anyhow, we work with rubidium-87 atoms. And we produce a lot of them in an optical trap. We place about 1 million or so rubidium atoms into an optical cavity, and then we go fishing. So we built this optical cavity in particular to be near the near concentric regime. And what that allowed us to do is to pull the cavity mirrors out to a large distance and open up a large numerical aperture to a high NA lens, which we could place looking at the cavity from the transverse direction. And with that high NA lens, we can project in these very tightly focused optical traps, which trap some, who knows, some number of atoms out of the optical dipole trap, maybe 1, maybe 10, maybe 1,000, I really don't have any idea. And then now we apply laser cooling to these tweezer-trapped atoms, and some magic happens. And the number of atoms in the optical trap in each of these optical tweezers is very rapidly reduced to either 0 or 1. And now you go ahead and do something like take an image and using information from the image and then resorting which tweezers are filled and which are empty, you can make deterministically filled arrays of exactly n atoms placed, in our case, along one dimension, wherever we want them inside of the optical cavity. So that's a pretty neat capability. Just again to go to some of the details, this is an experiment where we're working with a cavity that just barely achieves the strong coupling regime for single atoms. And so here's kind of the details on the experiment. Okay, so now we have atoms inside of an optical cavity. The cavity is about 1 centimeter in length. The microscope is looking at the middle hundreds or so of microns of this cavity. So the atoms are sitting here in an array along the cavity axis right in the middle of the cavity, and we're ready to do some cavity QED experiments. And as we develop our agenda in the lab and what kind of experiments we want to pursue, we sort of think about 2 different directions to take. One of them is, now let's think about using the powerful effects of cavity QED to improve the physics of working with atom tweezers, maybe to improve the performance of tweezer-based quantum simulators and quantum computers and stuff. And we have, some work along that direction. I mentioned that we've done measurements where we can measure the state of a single one of these tweezers while the atoms in the rest of the tweezers remain quantum coherent. So that certainly seems like it'll be useful eventually for something like a quantum computer. Or we can just keep being interested in quantum optics itself and think about how tweezers can push us ahead in our experimental capabilities to explore new regimes of cavity QED. So that'll be really the focus of what I'll tell you about today. And the story I'm going to tell you about today is a story that we've developed jointly with a few people in the audience. You're going to see a number of photos of them, and you can laugh about it afterward. Okay, so these are our friends at Columbia, Anna Stewart, who is not here, and Cosimo, who's also in the audience. And mostly been focusing on this particular setup. So we imagine that inside of our optical cavity, as I promised you, we've placed a number of atoms inside of optical tweezers. And so each of these contains just a single atom, and it's positioned exactly at some programmed location inside of the cavity. Now we illuminate these atoms with light that comes in from the side of the cavity. We actually illuminate them with a standing wave, but it's just a little easier to draw that it's a propagating wave. So let's imagine there's a plane wave driving these atoms, and we locate these atoms at present at locations where that plane wave all has a uniform phase front. Now these atoms might scatter light into the cavity. The light is somewhat near detuned to an atomic transition, so the atoms can scatter light into the cavity. We should think about how strongly they're coupled to this cavity into which they might scatter light. So the cavity field, remember, it's a Fabry-Perot cavity, so that's a standing wave mode of light. Here's the electric field of that mode. It has nodes where the field goes to zero, and it has antinodes where the field can either be positive or negative. So I'm just kind of shading them with different colors. And if you will, this is the Hamiltonian that describes the physics. Of course, it's an open system. It shouldn't be described by a Hamiltonian, but this is the Hamiltonian part of it. We're driving our cavity or our atoms with light that is somewhat detuned from the cavity resonance. So that's, in a rotating frame, the cost of photons. We have atoms in a tweezer in a harmonic oscillator trap. It's not exactly a harmonic oscillator, but there are mechanical degrees of freedoms for these atoms, and we'll just consider their motion along this one dimension. And then finally, we have this term, which describes the coupling of the pump light into the cavity. And includes terms like this one, where one pump photon would be destroyed, one cavity photon would be produced, and the strength of this term depends on where the atom is located inside of the cavity. So this is written as a summation because, of course, all these atoms scatter simultaneously into the same cavity field, which is to say that their emissions all add up in some coherent manner. And you can see this quite evidently. Let's say we place our atoms, let me just shift the tweezers and place the atoms at antinodes of the field, and in particular choose to place the atoms at antinodes where the field, the cavity field, has the same positive large value. So now I expect the sum of the emissions to be, or the emissions to be coherent with one another. The electric field inside of the cavity, or the amplitude of the cavity field, should scale with the number of atoms, which is then to say that the intensity of light in the cavity and the rate with which photons are leaving the cavity should scale as n squared, which is this kind of classic prediction for things like Dicke superradiance. So let's see how well this works in our experiment. Let me start with something simple, which is just two atoms, and take a two-atom tweezer array, place one of these atoms at one of the antinodes of the field with, let's say, a positive value, and then take the second atom and just scan it through the cavity and look at the total emission rate of light from the cavity. So this is what we observe. And as we scan that atom, we see certain locations, let's say, when the second atom is exactly an integer number of wavelengths away from the first atom. And at those locations, you see that there's a higher intensity of light coming out of the cavity. And scaled to how much light a single atom scatters out of the cavity, we see an emission rate which is, well, not exactly 4, but close to 4 times as much as a single atom scatters. And that's what I would expect, right? 2 squared is 4, so I'd expect that these two atoms would scatter coherently and we get 4 times as much light coming out. We don't get exactly 4, and that's because these atoms are not pinned at specific locations. They're rattling around inside of their tweezers, and there's some kind of Debye-Waller effect that reduces the coherence, and that explains the suppression of this collective enhanced emission. Alternately, if the second atom is placed a half integer away from the first, so that it's, let's say, at a negative valued antinode, whereas the first atom is at a positive valued antinode, then the emission should cancel out. And ideally, we would have no light coming out of the cavity whatsoever. We see less light than two atoms independently would emit, so that's kind of a sub-radiant response. And for the same reason I explained to you earlier, we don't see exactly 0, we see something a little bit above 0. So great, now let's turn this up to 11, or actually just up to 8, and increase the number of atoms stepwise. So here's a set of data where atoms are placed at integer wavelengths inside of the cavity, all at antinodes of the same sign. And ideally, we would see an emission rate from the cavity that scales exactly as n squared. So I can look this up. 8 squared is 45. So that's pretty close. And again, the lack of agreement with the cleanest result is explained by a Debye-Waller effect, the rattling of atoms inside of their cages. There's a subtlety to these data, which is sort of something that atomic physicists might like to think about. Please.
But the Debye-Waller factor, is it thermal rattling or spread of the wave function?
It's both, but it's probably dominated by the thermal motion.
So even if it was in the ground state of the tweezer, you would have a reduction of contrast?
Yes, I believe so. I think so. Right, so I'll just point out that it took us a while to figure out that these data should be taken at exactly 511 megahertz away from the D2 transition. This turns out to be kind of a magic spot for rubidium atoms where, in spite of the fact, as I'll show you later, that there's 5 different ground states in the F equals 2 manifold and 7 different excited states in the F equals 3 excited state, nevertheless, as the atom is rattling around all these magnetic sublevels, at this particular detuning, it doesn't make a difference, and the atom scatters like a 2-level atom faithfully. So that's kind of nice that you can reduce a really messy atom to just 2-level physics, and then all the papers that you theorists write are actually relevant again. So it's really convenient. I also really like these data down here where we spaced atoms by half-integer wavelengths. So again, let's go through the description. If I have 1 atom in the cavity, it scatters light. If I have 2 atoms spaced by a half-integer distance, they should scatter no light at all. And if now I add a 3rd atom, then the first 2 atoms have already canceled out each other's emission. So the 3 atoms should only scatter as much light as 1 atom. So we don't see, again, because of the Debye-Waller stuff, we don't see exactly that, but we do see this alternation between high and low, depending on the parity of the atom number. And it's really kind of a nice hallmark of more the subradiant nature of cavity scattering under those conditions. Okay, so that tells us that atoms are all scattering collectively into the cavity, and now let's think a little bit more about what that does in terms of their atomic motion. And so this term over here, which describes the collective scattering of atoms by light of pump photons into the cavity field, also happens to describe the energy that those atoms experience because they're in the presence of that light field. And the fact that there's a position dependence over here means that the atoms experience forces when they put light inside of the cavity. So when the atoms are sitting at these nodes, nominally they should not be scattering any light into the cavity at all. So I should be able to ignore this term altogether because there's no light in the cavity. But if some fluctuation should come around, let's say somebody bumped the experiment, and all the atoms happen to move a little bit in one direction, then now they're all, as I've shown you, collectively scattering light into the cavity. So now there's a coherent cavity field. That coherent cavity field interferes with this pump light and produces an optical lattice. And that optical lattice has forces, optical forces, and the atoms move. And they move, in fact, further in the same direction that they fluctuated to begin with. And this instability leads to like a self-organization of the atomic gas, where a fluctuation will be amplified, and all of the atoms will pick to move, let's say, to the right, all collectively. Or maybe on a different run of the experiment, they will all move to the left collectively. And people have examined this and found that it connects to something called the Dickey model and the Dickey phase transition. So I'm just like a caveman experimentalist. I know like nothing, right? So I need to find out what is the Dickey model. So I travel to where the Dickey model is very well thought of. It's in New York City. I go visit my friends out there. And they're like, Dan, we will show you the Dickey model. Just put on these glasses. I'm like, what? So there we are, we're wearing these goofy glasses, and I'm learning about the Dickey model. Well, in fact, we're looking up at the solar eclipse, which happened to be passing by just as I was passing by. But even so, they were still teaching me about the Dickey model. Okay, so here's these guys have heard this, but this is how it all connects. So, you know, the reason why we're wearing these eclipse glasses is because we're told not to look up. If you go outside, it's very sunny, don't look up directly at the sun. It'll burn your eyeballs, you won't be able to do much quantum optics anymore. And so that's not good. And also, if you just block that part, you will also notice something really interesting, which is the sky is blue out there. It's gorgeous. And you all remember why the sky is blue, right? Yes? Who doesn't remember? I'll explain it to you. Okay, anyhow. The sky is blue, sunlight comes in, scatters off the air, you see it blue. Lovely. But when the eclipse happens, it turns out you can take off your eclipse glasses. And then what you see is this. Well, that's not what we saw. We weren't right under the eclipse. This is what you would have seen if you went up to Maine. You see like the sun, it's blocked by the moon. It's amazing. And you see these like coronal jets. It's gorgeous. And if you look over here, it's dark and you can see the stars. So my next question is, why is the sky dark? Why is it dark?
No sunlight.
No sunlight. Yeah, great. Okay, great. All right. So here's how this connects to the Dickey model. Okay. So the outer space is cold. So we're presumably looking at a really cold space. Somewhere very cold, let's say call it 0 temperature. But we're also quantum opticians, so in this space, let's remember that there's also modes of light, and those modes of light have this Hamiltonian, so here's the energy cost of producing photons. And out there in outer space, it's not all vacuum, there's some atoms rattling around, and you can think of them as quantum emitters, so there's a bunch of atoms sitting out there as well, and here's their energy. And the idea is that, well, it's really cold, and so I just have to minimize this Hamiltonian. At 0 temperature, there's no photons, there's also no excited atoms, the sky is dark. Great. But we also have to remember that the emitters couple to the light field. So in addition, there's a coupling, there's a quantum electrodynamic coupling between light and matter, and here's that term. And notice this term, which couples the electric field of the light to the collective dipole moment of all these emitters. This thing can be negative. This energy can be negative. And in fact, if I turn up this coupling strength high enough above some critical value, then the night sky would not be dark. The night sky would be full of photons. That would actually be the lowest energy state. And this is, in fact, this is exactly the Dickey model. And as was described by Hepp and Lieb, this Dickey model has a phase transition as a function of this coupling strength. You go from a dark sky to a bright sky. You go from a normal phase where there's no coherent electric field out in outer space to the superradiant phase where there is. Okay, so that's now a nature question. Is the sky dark or whatever? So like, well, obviously the Dickey phase transition does not occur in the regular night sky. And the reason is that there's just not enough stuff out there. So if you got a density of atoms that was so high that the atoms were spaced by the Bohr radius, that was the basis of my answer, then yeah, the night sky would be very different. But that's not really what happens, and so we don't live in a superradiant universe. Nevertheless, it's an interesting topic for things like experiments, and so people can rig up experiments where we can effectively lower the energy of light. We can lower the energy of driving transitions on an atom, and then even in like the conventional coupling strength between light and matter, we can drive the Dickey superradiant phase transition. Okay, that's a long-winded story. It's been done. It's been done previously in a number of experiments. The ones that are most relevant to what I'm telling you are these experiments by the Esslinger group, where they placed a gas of many atoms inside of a cavity. They exposed them to a standing wave of light. And above a certain coupling strength or a drive strength, these atoms suddenly broke a symmetry. If I just think about this one line here, you see that all the atoms can choose to jump either to the right or to the left. And in doing so, they will induce an electric field inside of the cavity that has either a positive phase or a negative phase, breaking a Z2 symmetry, and that is indeed the Dickey phase transition. And these experiments were done with a very large number of atoms, so clearly in the thermodynamic limit, and that's where the experimental work has been done so far. And what we're bringing to this problem is returning to the Dicke phase transition, but in a very mesoscopic regime with a fixed number of atoms and therefore also a great deal of control. Now, here's a theory slide, and I always want to skip this, and I'm going to skip it once again. But basically, it's just sort of asking, how is it that you go from this optomechanics model to the Dicke model? And I can just sort of trace our steps. One of them is you get rid of a sign, which is the modulation of the cavity field, using the Lamb-Dicke approximation. That now turns into an equation which is like a harmonic oscillators version of the Dicke model, which is also interesting to study. And then finally, if you happen to be at very, very low temperature and you can regard just the lowest two levels of your harmonic oscillator, then you really are looking at the Dicke model, and then the mapping is really complete. And I bring this up because neither of these approximations holds strictly in our experiment, so take a lot of grains of salt. I will point out that we think that there's a lot to do in our experimental setup because the range of things that we can bring about in our system. And then I also want to bring up this nasty expression down here, which is a prediction for what is the critical Rabi frequency at which the phase transition occurs as a function of a variety of parameters, including the detuning from atomic resonance with which you drive your atoms and the number of atoms with which you're going through the phase transition. And so these are two specific dependencies that we'll check out in our experiment. Okay, so here's how we do the experiment. We take tweezed atoms, we place them at nodes of the cavity field. As shown in this graph here, we place them at half-integer spacings. One advantage that gives us is that the system is now immune to center of mass displacement, so it's just much more robust setup. And then we drive atoms with light from the side, and we look at the emitted light, in our case on a heterodyne receiver, that allows us to measure the two quadratures of the cavity field. And by doing some calibrations, we know in what quadrature the symmetry-broken cavity field should show up. You can also see it by looking at just data from an experimental run, where here the different data are sort of color-coded with time advancing probably from light to dark or something. And so you see the cavity field largely fluctuates along this quadrature, and that'll be what we'll call the real axis for the electric field inside of the cavity. So let me just plot the amplitude along this quadrature, and that's this trace right here. So we ramp up the strength of this driving field within the first, I think it's about 50 microseconds, and then we just look at it as a function of time. And so this is a trace taken above the phase transition. And you see that, look, all the atoms have jumped into, I guess, the red side of the cavity, and I guess they've produced a positive valued electric field coherent state inside of the cavity. Oh, but then they decided all to jump to the other side, and now they're in the opposite symmetry broken phase for this particular trace. So I'm going to take these data and just bin them up over very short time bins. So that gives me a number of data points. And then I'm going to run the experiment many times. That gives me a lot of data points. And then I can just plot down a histogram of what I see. And what I see is this. So as a function of the drive strength, we see that at low drive strength, the electric field remains kind of near the vacuum state. At a high drive strength, we see that the electric field inside of the cavity has a large coherent state amplitude that is either positive or negative, and that is directly viewing the symmetry breaking of our physical system. I am going to need more time, so maybe I'll just gobble up a bunch of the discussion time. Sorry about that. Of the discussion time with questions. I'll just do that. Okay, so sorry about that. So here's the data. Here's actually the histograms that I showed in that previous color plot. This is a histogram of the data below the phase transition, and as you go above the phase transition, you see that the distribution bifurcates, and you see this symmetry breaking. Now, how should we understand this distribution? What are we looking at? So I go look up some textbooks about phase transitions, and this is what I see. There's a standard theory for phase transitions, which considers the free energy of the system. And its kind of conventional model would be a free energy that contains a quadratic and a quartic term in terms of the order parameter. And the transition occurs when the sign of the thing in front of the quadratic term flips. And now, rather than having a single minimum where the order parameter being preferentially at 0, you have two minima with the order parameter in this Z2 case being either positive or negative. Now, Ginzburg's amendment to Landau's theory of phase transitions was to consider whether or not the order parameter should be a fluctuating quantity. So in Landau's theory, it's just a number, but in Ginzburg's theory, we asked, does it actually fluctuate? For example, as a function of position, but also as a function of time. And one of the powers of Ginzburg's theory was to think, as my system gets larger and larger and larger, and I think about all these different patches of fluctuating order parameter, do those fluctuations matter in the end? Or do they just sort of average out to something that is pretty close to what Landau said? And that leads to a prediction, if you recall your stat mech classes, of something called the critical dimension. And above the critical dimension, you can just consider the order parameter to be a mean valued object. But below the critical parameter, you have to keep thinking about fluctuations. The Dickey model is like an infinite dimensional system. Everything's coupled to everything, so it's clearly above the critical dimension. And so the macroscopic Dickey model would be well described by mean field theory. But for a mesoscopic system, there isn't an infinite size limit, and so the fluctuations, at least close to the phase transition, are also always important. So that's kind of a hallmark of our system. Now, if the fluctuations do occur, we have to think what distribution might they follow. And perhaps just simply, I'll think that they follow a Boltzmann distribution. So we're going to take these data and fit them to a Boltzmann distribution of this type. And from that, extract these capital B's and D's, which I can think of as being lowercase b and d divided by the temperature. Okay, so first of all, I'll show you the fits work quite nicely, and we can extract, for example, the quantity B, and we can find out now very precisely where it flips sign. That's basically when the histogram looks like it first develops its little divot. And now I can tell you what is the critical coupling strength as a function of number of things. So for example, we can look, how does the critical coupling strength vary with atom number as we look at systems that range from 10 to 22 atoms. And it matches reasonably well with theory. This is what we would have expected given a pre-measured temperature for the atoms rattling around in the traps. The data are somewhat above that, maybe indicating that we don't understand our system well, maybe indicating that the atoms heat up during the experiment. We don't measure the temperature very well. But nevertheless, we do see a variation with atom number that's fairly consistent with this square root of n dependence. There's also this dependence on transition, on the closeness to the atomic transition, but I'll skip those data. Maybe I'll say the following also. Are there any theorists in the room? Okay, right. So this is what you would tell me. You would tell me that, listen, Dan, phase transitions occur strictly only in the thermodynamic limit. And that is a true statement. Yes, but it should be qualified by paying attention to how much time I have left in this talk, right? So phase transitions only occur forever in the thermodynamic limit. You should really ask yourself, how long do I want a broken symmetry phase to persist? You know, if you're asking, does symmetry breaking occur and it lasts for an entire year? Then yeah, you need a really, really big system to remain persistent for an entire year. But if you're asking, does something break symmetry for like 5 microseconds? Then actually, you know, really small systems would be regarded as breaking symmetry and undergoing phase transitions as well. This physics becomes evident in let's say, the physics of nanomagnets, which have been studied in a number of experiments. And there they see a phenomenon they call superparamagnetism. And I'll describe to you what it is. So as a function of temperature, you find that you have a paramagnetic phase, and then as the system goes below the bulk Curie temperature, you get to a point where the nanomagnet is now, all the spins in the magnet are bound to each other, but the entire spin of the system is still fluctuating around like crazy. So it's a paramagnet. I mean, it fluctuates slowly, but it is a paramagnet, and the fluctuations are large. That's the super part of it. And only at a lower temperature called the blocking temperature does the system become ferromagnetic. So again, if you looked at your magnetic system only looking for persistence over a particular time scale, that time scale would define when you go from the superparamagnetic to the blocked phase, where you no longer see fluctuations at that time scale. Okay, so that's what we see in our experiment. So first, again, these are the kind of trajectories that we see in individual runs of our experiment. Sometimes we find that the system breaks symmetry and remains in the broken symmetry state forever. Sometimes we see that it doesn't stay there forever. Maybe it switches from a positive to a negative broken symmetry state. Sometimes it cruises around like crazy from positive to negative, presumably indicating that in this free energy diagram, the thing is just rattling over the top. Okay, so we see all those kinds of trajectories in our system, but let's just ask this question of how long the symmetry breaking persists. So,
how deep are you branching inside the superconducting phase? How deep are you branching inside the superconducting phase? How deep?
it depends where. I mean, this is somewhat deep. Well, as I can tell you, somewhat deep.
Somewhat deep.
Yeah.
You are not close to critical.
Not for these particular data. So let me show you these data in particular. So here's where we're asking, remember that previous measurement of like when does the distribution bifurcate? I can bin my data in small time bins, and then I see this critical value for the phase transition. Or I can bin my data over long time bins, like 50 microseconds, and then I see this critical value for the phase transition. Okay? So essentially, let me look at like n equals 14. This is sort of telling me that with 50 microseconds being the time over which I consider it to be a phase transition, this is the paramagnetic phase. We're below the phase transition. This is superparamagnetic. Over short time scales, we see very large fluctuations, but at long time scales, we don't see retained broken symmetry. And only above here do we really enter the broken symmetry phase. And you see, as you see in nanomagnets, that the separation between the Curie temperature and the blocking temperature, or the Curie critical value and the blocking critical value, becomes smaller as the atom number gets bigger as you go into the thermodynamic limit. Okay, we've also measured, I don't have time to talk about it, we've measured the mechanical susceptibility in our system, which we do by displacing the tweezed atoms in their traps, and by measuring the magnetic mechanical susceptibility of our system. We see some, clear evidence of mesoscopic fluctuations. I'll have to just describe that separately to you. Last thing I would have liked to tell you, but cannot for lack of time, is that we also have an understanding of how to realize the Dicke phase transition not in the mechanical sector but in the spin sector. It's actually a very simple modification of our setup that involves, let me skip. Placing atoms in an applied magnetic field, driving them with polarized light, and then paying attention to the fact that the cavity carries two different polarized modes. And when the atoms undergo symmetry breaking, they'll create an interference between the drive field of one polarization, the cavity field of the other polarization, which locally generates a circular polarization, which acts like a magnetic field on the atoms and tips their spin. It ends up being the exact same dynamic as we saw in the mechanical version of the Dicke phase transition, with some nice wrinkles that we can look for both the breaking of a Z2 symmetry, where spins pointing down will sort of choose to go left and right, or also a U1 symmetry breaking, where spins along the cavity axis will spontaneously tilt in some direction. And I think we have a handle on, we've also seen to some degree experimental evidence of these transitions already. So sorry for going over time. Let me thank again my group, thank my wonderful collaborators who teach me so much. I did not have a chance to tell you about experiments on laser cooling atomic titanium. You can ask me about that. I did not have a chance to tell you about our experiments on atoms in optical lattices. You can ask me about that also. Thanks a lot.
All right, Anna Maria? Very nice, Dan. I have a question. So when we were doing these experiments with trapped ions, there was no dissipation of the phonons because they don't dissipate. And what we were seeing is that the transition, the fluctuations that you see in the transition depend a lot of the number of excitations that you have in the motion. So, for example, we go from quantum fluctuations denominated across the transition to thermal fluctuations. The question is, well, you have an open system, and all the descriptions that you make for the decay model are not, because these are for the ground state.
Yeah.
Not for an state, well, or maybe they apply for an state space, but it's different because you are having a system that is open and you go to a steady state. So do you know how the nature of the fluctuations are going to be modified when you don't have a real equilibrium phase transition to something that is more steady state, and how they are affected by the dissipation?
Yeah, good. So there are theorists in the audience who could probably answer this question really well. I'll just answer it in my own sort of caveman manner. So one picture would be that we should, especially after we've shown a bunch of light on our atoms, we should not expect our system to be really a quantum zero temperature system anymore. It should be considered at finite temperature. Maybe it's a transient problem. Maybe we're starting cold and it's just getting hot over time. Maybe it's just an optomechanics problem, and that eventually the system is going to come to some steady state at a temperature given by h bar kappa, right? The cavity line width. Those are all possible ways to describe what's going on. And then I've made a lot of glib assumptions in here about thermal equilibrium, a statement about the fluctuations of the order parameter, a prediction for what we should see for the mechanical susceptibility. All that was just guessing from a particular thermal distribution, but it's not entirely clear, you know, that those that should be really the strictly correct description. I mean, it kind of fits, right? But I think we haven't quite done this as a theory experiment comparison this rigorously yet. But if we really look carefully at these fluctuations and their time scale and everything, can we actually understand everything that's happening there as a thermal model or not? And understanding, you know, symmetry breaking and activation over a barrier is already interesting, I think, in a thermal equilibrium system, but it's perhaps doubly interesting in a system that is actually open and dissipative and so forth. So that might be scientifically what makes it the most interesting.
Okay, but you have not seen very clear difference between...
No, I don't think we have the ability, maybe because the temperature is kind of high, maybe the differences are going to be kind of washed out, maybe we're not looking at the right thing yet.
Thank you.
Yeah, thanks.
Okay, I'm going to apologize ahead of time for the unfairness of exactly who caught my eye in which order, but I think Helmut had a question, and then Arno, and then there's a very long waiting list after that. Or never mind.
Yeah, cool stuff. So there's many questions, but I'll have only a few. I mean, you mentioned that you don't get to 4 in the beginning or 0 there, and 1 is, of course, the delocalization. But another thing is that I think Giovanna calculated once is that once there are atoms in the cavity, it's not as a good cavity anymore, which makes one difference for the 4. And also for the 0, it's not for photons, it's zero field. So there still are photons, it's just that the average field cancels, so it shouldn't go exactly to 0. And that would be an interesting part to study the properties of this remaining field. And I don't know how hard or good this is.
At that point, we were measuring it with a single photon counter. It was near 0. There is, of course, a little bit of just the noise, right? I mean, what we saw was a field that had 0 average. That's for sure. When we looked at it again with the heterodyne receiver, the field was fluctuating around 0 and had kind of largish fluctuations, and that gave an overall photon flux that we saw. So those things are connected to one another.
Should be pair photons or squeezed photons?
Oh, I see. Yeah, that's quite interesting. The second point, that the atoms kind of spoil the resonance of the cavity, that's true. These experiments were done with light that was 500 megahertz detuned, so I think it's not an issue, not a large impact. But there's no reason, in fact, we took the data also very close to resonance.
If you have enough atom, it levels off, sort of, because
Yeah, thanks. That would be good to look at more.
Okay, I think Giovanna had a question. Okay. Okay. Dominic also had one. Sorry, I have a waiting list in the back of my head.
Hi, Dan. Just a quick question.
Yeah.
So, at the critical point where you're susceptible to fluctuations, have you thought about doing some kind of modulation of the traps to stabilize?
Yeah, that's a cool question. Not so much have we done a modulation of, that's a really interesting idea. Yeah, so if we're at or even above the transition, we can do some kind of modulation, you know, which whatever stabilizes an upside down parabola. And then we've also been thinking about feedback stabilization. And so, yeah, that we're building that into the system now. And I think it should be quite interesting to look at this phase diagram and then basically like tune a parameter on a feedback circuit, right, and see the phase diagram move, or maybe go from second order to first order or something that would be pretty distinct. Yeah. That answer the question? Yeah.
So actually, it follows up the question on critical points. So if you could quench close to critical point, you should see an extreme strong sensitivity to the size n, and there are theory predictions for chaotic behavior that you would see in the quadratures that you measure of the photons. So you would see a Lyapunov respondent that comes only from the fact that you have finite n. So I think you could, with the stuff that you are computing, see something theoretically very cool. The question is, do you have any limitation on going close to the critical point? So like running dynamics very close to it, such that, you know, in your picture, you are close to a separatrix. You are close between a phase that is 1 minimum and a phase of 2 minima, and any finite n that are effective h bar will make you ultra sensitive. And then, I mean, there are plenty of theory papers that go around that, and nobody, I think, would have seen it in experiments before, because, as you said, everything was macroscopic. So, like, if you could do that, I think that would be really exciting.
Sounds great. I wasn't aware of that particular prediction. The question you were also asking was how close to the critical point we can go. Well, I don't know. You saw how closely we can figure out where it is. We can go anywhere we want, you know. So the errors in that in that determination of the critical value are pretty small. Yeah, I don't know. I guess I don't have a really fixed answer how close to the critical point we can get. I do think that there's this interesting, you know, how does a theorist simulate a phase transition, right? So you usually on your computer you study a little block and a bigger block and a bigger block, and then eventually you do like you just kind of see how it scales with n, and you project out to n equals infinity. And I like the idea that we can actually experimentally do that finite size scaling, which otherwise is just a numerical tool, and really look at phase transitions and what is their finite n scaling. It's an attractive research direction.
Okay, I think we have time for one more, and then.
Dan, thanks a lot for this beautiful results. So if I understand correctly, in all of the things you showed, you were very far detuned from the atomic resonance. And so you are diabatically limited. The internal states don't play a role. So I was wondering whether I can think of it as if basically the laser, you know, is far detuned from the atoms, and it heats them, but just like in laser cooling theories, and you get a temperature. And just I can think of it as like this classical, I don't know, system of, I mean, just you have temperature from the laser cooling that you can get, and then maybe these jumps, could you, I don't know, get them from like Krumm's problem, you know, jumps between two potentials where you have the temperature. Can you think about it classically in this way? Would it be helpful? I don't know.
Yeah, I mean, I've mostly been giving you a presentation which was entirely thinking about it classically. And you asked how close we are, you know, so we've looked at the transition fairly close to atomic resonance. I mean, there we are at 40 megahertz detuning. As we get closer to the resonance, what we find is that there's another term in the Hamiltonian, which is the cavity pulling due to the fact that the atoms are in the cavity. And that modifies the interpretation in terms of a Dicke phase transition. It still supports the existence of a Z2 symmetry breaking, but it like moves you to a different point, or maybe sharpens the transition. So we tried to avoid going very, very close to atomic resonance. It's interesting to think about, you know, regular laser cooling while we're also driving this transition along the lines of what you're thinking about.
So I mean, I guess what I'm asking, maybe I don't understand the details, but I mean, eventually these jumps you have between the two steady states, maybe they're activated, as you say, by something like a thermal noise. And then if you can associate a temperature to that, maybe you can also predict the rates of these jumps or whatever.
Yes, yeah, good. So that's exactly something we'd like to do. It was kind of in my next step slide. I mean, I think if you look at the literature on like nanomagnets or mesoscopic systems, you see a lot of experiments that have looked at like this Arrhenius behavior, right? As you change the height of the barrier, change the potential, you'll see this, Boltzmann-like change in the transition rates. One thing that's interesting is that usually in the literature, they don't tell you what the prefactor is because it's kind of this mystery thing, but they just say, well, at least it scales correctly. And I feel like this is such a clean system, we should be able to predict everything about it. And it might be a nice test case for thinking about some of those things more precisely. Yeah.
Okay, so with that, I think we need to wrap up. So let's thank Dan again.